Our next presentation will be waste minimization through efficient spray finishing. It will be presented by Steve Kish, who is Market Development Manager for Graco Incorporated. He's had 2.5 years in this position with a primary focus on aerospace, wood furniture, farm and construction equipment, rail car, and the defense industry. He has 20+ years in sales and market management positions in the coating industry, a Bachelor of Science from Michigan State, and graduate studies at Clark University. Welcome, Steve.
Well, thank you, Cam, and hello, everyone. It's a pleasure to be with you this morning. I would like to take this opportunity to talk about 4 topics that relate to the stated theme of waste minimization. These 4 topics are transfer efficiency, operator spray technique, HVLP, and the electrostatic application of paint. In this session, we will concentrate on the issues of transfer efficiency and proper operator technique. In later sessions, we will explore the various methods of spray atomization, including compliant methods like HVLP and electrostatic painting. Transfer efficiency is an important consideration when a company's goal is to minimize the generation of hazardous waste materials. Basically, transfer efficiency is the amount of paint that actually lands on a part compared with the total amount of paint being sprayed from the gun. The formula that expresses this relationship is as follows. TE, or transfer efficiency, is equal to the weight of the paint solids, WP, deposited on parts after baking. The percent solids, or the apostrophe S, is equal to the percentage of solid paint sprayed. O is equal to the paint flow rate, and T is equal to the time that the paint was being sprayed. Our goal then is to maximize transfer efficiency and to minimize the amount of paint used to paint a part. Higher transfer efficiency will result in lower paint costs, fewer solvent emissions, reduced exposure by plant personnel to solvent fumes, less sludge to dispose of, and less maintenance and less paint handling in general. This task is complicated by the demands of real-world production requirements. Typically, test data on transfer efficiency is gathered in a laboratory environment where conditions are static and idealized. Actual conditions on an industrial finishing line vary greatly from plant to plant and even from operator to operator in the same plant. This is why tests for transfer efficiency often report extraordinarily high numbers when compared to results in the spray booth. Now, Graco uses a test method that is designed to determine the transfer efficiency of the type of application tool. This method, we remove the variables of operator technique, airflow past the booth, part configuration, and so on and so forth. The test that we use calls for painting a group of 10 4-foot by 6-inch panels that are wrapped with pre-weighed aluminum foil, and they're hung on 12-inch centers on a moving conveyor line. The painting is performed by a test gun that has been preset to approximate the demands of a production environment. We trigger the gun 6 inches before the spray contacts the first panel and release the trigger once the last panel has moved 6 inches beyond the gun. By doing this, we can accurately determine the amount of paint dispensed through the gun and compare that to the amount of paint by weight that ended up on the panel. We determine the weight of the paint on the panel by first drying the paint and then weighing the aluminum foil after the paint process has been completed. We note the difference. By using this method, we are able to provide a realistic figure that one can reasonably expect from each method of spray finishing. By using the same test criteria, here is how the various spray technologies performed. Conventional air spray, 30% transfer efficient. HVLP air spray, 40% transfer efficient. HVLP air-assisted airless spray, 45% transfer efficient. Electrostatic air spray using a 65 kV generator, 65% transfer efficient. Electrostatic air-assisted airless spray, 70%. And finally, electrostatic air spray using an 85 kV generator is 75% transfer efficient. I would like to point out that the maximum TE that can be achieved using non-electrostatic application device is 50%, since the gun is on target only half the time. In order to achieve a TE of greater than 50%, you must use electrostatics to draw paint particles onto the part that would normally miss the target. But please remember, this is a laboratory method designed to test relative performance levels. However, I can tell you that this test method has been shown to be very useful, both to us and to end users. These findings have been supported by field results. We know of an aircraft painting operation that was able to achieve a 40% material savings when they switched from conventional air spray to electrostatic air spray. But as we have already noted, in the real world, spray finishing conditions are much more complex. In addition, the industrial finishing line is governed by two overriding concerns: finish quality and productivity. The finished appearance of the product being painted is essential to its success in the marketplace. The need to provide a finished quality in as short a time as possible is essential to keeping production costs down. These two factors will determine the selection of the finishing tools and the way they are used on the production line. To minimize the generation of hazardous waste, the objective should be to maximize transfer efficiency without adversely affecting either finish quality or the speed of the finishing line. We at Graco have identified 10 factors that have a crucial effect on transfer efficiency. They are: operator spray technique, fluid delivery rate, atomizing air pressure, target size, type of application tool, condition of the application tool, configuration of the target, air velocity in the spray booth, fluid pressure, distance of the spray gun from the target. The most critical factor in a manual finishing process is also the most sensitive, namely operator spray technique. Good spray technique can maximize the transfer efficiency of a relatively inefficient spray gun. Bad spray technique will certainly reduce the transfer efficiency of an otherwise efficient tool. That is why the key responsibility for waste minimization in the spray booth rests with the operator. Here are a few of the key elements of a good spray technique that will maximize transfer efficiency. Gun setup. Make sure that the coating being used is properly atomized at the lowest possible pressure to maintain your finish quality and line speed. Too often, operators will simply increase pressure to achieve fine atomization rather than thin the material to aid atomization or to clean the gun of obstructions that affect atomization. Proper gun position. Hold the gun perpendicular to the surface being sprayed to reduce uneven paint coverage. Proper spray speed. Ideal operator spray speed varies from 2 to 3 feet per second. Slower speeds result in runs, faster speeds result in inadequate coating of the target. Proper distance from the target. The distance of the spray gun from the target should remain constant. Keep the spray tip of the gun approximately 8 to 10 inches from the surface during each spray stroke. Adjusting the fan pattern. Make sure that your fan pattern is properly aligned. Typically, you will want to spray a vertically shaped part with a vertically shaped fan pattern. And cleanup. Cleanup is essential to proper and efficient operation of any finishing tool. In order for a premium finishing tool to perform at its highest level of efficiency, it must be correctly cleaned and maintained. Make sure that your painters perform preventative maintenance every day to ensure total performance. In some states, open-air flushing of spray guns with solvent is prohibited. For these areas, self-contained gun washer systems will be necessary to keep your spray guns in prime operating condition.